My name is Johannes Doerfert. I work with HAL at Argonne. And I'm talking about optimizing indirections. And the first thing, I really appreciate that people pay me to do this. So let's look into context and motivation. So where I come from, I'm actually looking into optimizing parallel programs. That is what I want to do. That is where I come from. Now, when you do that and you look at that quite a while, you realize you want to do two things. You want to optimize the sequential aspects and the parallel aspects, okay? Now, if we want to optimize sequential aspects, we can actually reuse existing transformations and analyses and optimizations we have right now because we optimize sequential aspects all the time in LLVM, so why not reuse those? For parallel aspects, we actually have to introduce new techniques because we don't have anything similar that does that in LLVM. You can look at that paper to get some examples. Now, this talk will actually be about the sequential aspect. So we want to introduce suitable abstractions and transformations to bridge indirections that come from parallel programming. So if you have a parallel program, you get indirections, you want to bridge those and actually optimize it. Now, if you want to optimize the parallel aspects, we also have a proposal for that. And if you're interested in any of this, please contact me. Please come to our BOF later today. Now, let's look at what we want to do. So we have a loop. And at some point, we realized that the variable y is actually constant. Now, we expect the compiler to replace all uses with the constant. Okay, so far, so good. But now the user thinks, okay, this loop is parallel, so I'm actually going to tell that the compiler, execute this in parallel. And the problem is this constant propagation is not going to happen anymore. And it's not going to happen anymore inside the parallel loop, but also outside the parallel loop, which is really, really bad. Now, this is where I'm coming from. These kind of optimizations are currently missed. And now the question that should be raised is this important, right? Because it's constant propagation, couple of things, whatever. We get scalable parallelism. But let's look, I did an experiment. So I took a couple of OpenMP benchmarks and I removed the OpenMP annotations and I ran them. And then I ran them with OpenMP annotations, but with one thread, okay? So the first benchmark is Lulesh, the OpenMP version. You get a slowdown of 3.6%. That is not that bad. You go further, you see BFS, other benchmark, you get a slowdown of 8%. Now, still, you could argue you get benefits from the parallelization later on. But as you go on, you see bigger and bigger slowdowns. 40% for Pathfinder, 140% for SRED version 2. It's the first thing you do when you introduce OpenMP on parallel 4 in your program is get a slowdown of factor 2 and higher, and then try to get that away by scaling the parallelism. That is what we do nowadays, because our compilers are not able to optimize parallel programs, and we get those slowdowns. Now, why is that? Let's look at how we currently translate OpenMP, but this is not OpenMP related. This actually boils down, everything boils down to exactly the same thing as I say here. It's just OpenMP because we load that and the examples are easy. Now, you have an OpenMP parallel for loop, and what happens is at the place where it is in the code, that is replaced by a runtime call. The runtime call has the loop bounds, a body function, and all the arguments that are captured, okay? This is just a simplification, but you get the gist of it. Now, somewhere else, there's this body function that is the body of this loop, which is outlined into a separate function, and there you have the actual loop now, and you get the loop bounds from the runtime, and you get the arguments that are passed, and then you can access them. Now, the problem here is that you have really weak connection between the arguments and the parameters here. So the parameters and the arguments, there's no mapping between. So the indirection comes from the runtime library call and the function pointer. So from the compiler perspective, we don't know that this will invoke this and that this in variable here will eventually become this in variable here. That is just, we don't know that. Now, parallel ARs, as they are currently proposed in different proposals, as they're proposed for a couple of years now, basically make this connection. So they make it clear that this in is this parameter in, and that the body function is eventually called here, potentially multiple times or one time, it doesn't matter, but they make this connection clear. Now, we don't want to go that far because that is if you do the connection clear, you also have to make sure that nobody can misinterpret this connection because that is not really what is happening. So because we don't have a concept of a par 4 in the compiler, we have problems here and we have to do the modeling with care. So you want to have a connection, but you don't want to expose it such that things can go wrong and actually you get unsound semantics. So let's step back a bit. And now what is happening here? The runtime call, we know, will eventually call body function and pass these arguments here, right? That is what we know will eventually happen. potentially multiple times, but that is what's happening. Now, let's model that. So there is a transitive call to body function where the first argument, we don't know what the first argument will be, so we just put in like a question mark here, but we know what the other arguments will be. Now, we have, like in our model, we have a connection between this runtime call, because we know it will transitively call body function and pass the following 3 arguments. And that is what we now will use. So the benefits of doing this, you always have valid intermediate representation that you can execute. So you can always, like, there's no post-processing needed, like, there's no intermediate steps, whatever. It's always valid. So I will never destroy any properties. You don't get unintended interactions between passes that you didn't look at, or corner cases you didn't look at, or passes that are downstream at like people's compilers, and so on and so forth. And you actually have a lot of function pointer arguments already in sequential code as well. So this has nothing to do with parallelism per se. Like transitive calls is just like a concept, a model of modeling the behavior of this runtime call. The fact that this runtime call will then start threads and those threads will do the transitive call in parallel is something we don't like care about at this moment. Now this is actually, like, that is really important. That is not an optimization for parallelism, but it's an optimization for transitive calls, which can also occur in sequential codes. Now, the downside is, if you do this modeling here, you actually have to enable inter-procedural optimization one by one. So you have to go to an inter-procedural optimization, and then you have to teach it about transitive call sites. Let's look at that. Currently, inter-procedural optimizations use Coldsite abstractions. So they don't look at the AR explicitly, which is already good for us, because they don't want to know if it's a call instruction or an invoking instruction, but they use a Coldsite. Now the passes just query the Coldsite to get the callee, the caller, the argument, the parameter, all that information they need, right? Now what we do is we have a transitive Coldsite that kind of derives from a Coldsite. So because the Coldsite is a direct call, and this is a transitive call that is done by the first level callee, will then invoke a call to something else, like a second level callee. Now, in order to make the passes use both, to be able to like not care about what kind of call it is, we introduce an abstract Coldsite, which just like is an interface for both, that just hides the fact that it's either a direct Coldsite, which is currently called Coldsite, or a transitive Coldsite. And now the passes can query the abstract Coldsite. Give me the caller, give me the callee, give me the argument and parameter. Now everything is as before, but you still have to do something. So you don't only have to introduce, replace all call sites with abstract call sites in the passes, but you have to do something else. And that is shown here for the function, for the interprocedural constant propagation pass. So interprocedural constant propagation is in LLVM, is not enabled by default, but it's a nice example. These two and these 2 lines are the functional changes I had to introduce to make transitive call sites work, such that the very first example I showed you with the 7 that is not propagated into the parallel loop will actually work now. Why is that? What is happening here? So the difference between a transitive call site and call site has to be cared for, and the difference is that the transitive call site doesn't have a full mapping between arguments and parameters. So it could be a partial mapping, and you have to take care if the parameter is actually mapped or not. So we check if we know the argument that is passed as parameter I. If not, we treat it as non-constant because it could potentially vary. We don't know what it is. And that is all we have to do, and then constant propagation into parallel regions works. It also works for other things that have transitive call site semantics. So this is all we had to do here. Now, we did that and had the idea of transitive call sites, and that is all nice and well. But then we realized, okay, inter-procedural optimizations in LLVM are not as strong as you want them to be. And that is kind of problematic. So let's look at them. This is an example. I'm not going to show all the codes, but this is an example with 2 strongly connected components. And you have 3 internal functions, 3 external functions. Source, it doesn't have any caller that is known. Sync doesn't call any function. Everything else is part of the SCC. And if the argument is called R, it means read only. If it's called W, it means write only. And if it's called N, it means read none. Okay? So, and I made sure that those properties actually hold. And you see ret2 means the second argument is actually returned by this function. So we could, all of that is known. I made sure that all of that holds. Now, the way I implemented it is basically like this. So you have sometimes some things that actually read and write, but then we actually just call the other functions wildly, right? So what happens? This is the call graph of the whole thing, like 6 functions plus an external node to keep them all together. And now we have a function attribute deduction, which like infers function attributes, argument attributes, what is returned by a function, all of those things we are interested in potentially if we have interprocedural, if we want to do interprocedural optimizations. And it turns out that except for the sync, we basically don't find out anything. That has a couple of reasons, and if you're interested in that, I would recommend to look at the RFC probably derived function and argument parameter attributes, which are on the mailing list. So far, not many people were interested in that, but as soon as we don't want to inline aggressively, we have to step up our interprocedural optimizations, which are currently really poorly. And for transitive call sites, I can't inline. It means that I need stronger interprocedural optimizations, and this attribute interference is really needed for a lot of things. So we need to interfere attributes like dereferenceable for a lot of things in order to do what I show next, which is, oh no, it is afterwards, sorry. So the next thing is constant propagation first. So interprocedural constant propagation, as I said before, it is done by SCCP pass. And now the question is, you have foo 2, 3, and here's the callee, or a pair 2, 3, and here's the callee. Will we replace that by 5 in both cases when we disable inlining? So there's no inlining happening, right? And it turns out, yes, we will. That works fine. Now we change the examples a little bit. Instead of a pair, we pass a pointer to a pair, but it's still a local pair. So we still have, like, we see that it's only the members are used, so all users are fine, it never escapes. And we see that it's actually dereferential, it's a stack allocated pair. So everything looks good here in this example. And here, it's not a pair anymore, it's a tuple with 4 elements, and we pass the tuple, right? What happens next? Obviously, we won't derive 5 for either of them, otherwise I would have chosen different examples. The point is, here, our pipeline is simply not, the pipeline is simply not good enough. So if you run the pipeline, O2's pipeline twice, you would actually get 5. But the way it's currently structured is not meant to do really good interprocedural optimizations, and we are just not able to do it. But we could. On the right, it turns out that the pass that is needed here to decompose the tuple will not do that, because the tuple has more than 3 elements that are accessed afterwards. And you know, it's always bad to decompose something that has more than 3 elements. And it's per argument. So if you have 5 arguments, all 3 elements, it will decompose all of them, obviously, right? So the lesson learned here is our pipeline is not really tuned for IPOs, and we also have passes that are written for a certain goal in mind. For example, like let's split up pairs, because pairs happen to be everywhere. So we have to have a pass that does that, and it does. But it doesn't split up anything else. So if you have a class object, a struct object of any size, you still want to do that. Now what I would propose to do is, it doesn't really matter how big the tuple is, I would propose to actually split it up. Why is this important? Look at a tuple that has also a pointer in there. And if we pass the tuple in here, like pass the t pointer to the function f, we basically have to assume that the pointer h escapes. It already escapes when we store it to t, but if we can make that connection explicit, because even this thing doesn't use h. So we don't know that here, and we don't have any facilities to figure that out here. So currently, we will just say, okay, the t of h is just escaping, and that's it. Now, if we split up the tuple at the callee and at the Coldsite, we can, first of all, we make sure that th does not escape, because it's never passed to f, which is a good thing. And then we can expose the fact that some of the arguments are actually constants. Now, we pass those constants along, and then we can decide at this point, because we did all this fan out, we might have a lot of arguments now. And that might not be good with our calling convention on our target, so we can decide to, let's have a pass at the end that condenses it again into compound objects, such that you don't have that many arguments to pass over, right? That is utterly feasible, and I actually have a prototype that does exactly this. So what I propose is aggressively unpack objects, because that is necessary for optimizing parallel programs, especially in real-world applications, and then condense the arguments at the end, after you know what arguments you actually need to pass and what is actually left. Now, There are a couple of other things that are currently ongoing or planned. So these are the three most important ones. So ongoing is the tracking of values of fields of struct members across function calls. So we have a prototype that does that. So you have a struct or an object and you pass that to a function and you know that that function will kind of write 5 into a field or write a global variable into a field or whatever. It will capture that and you can use that at the Coldsite again. So that is something that we will need for closures. So if we optimize OpenMP tasks or other kind of tasks and you build closures in a separate step, then you need this. So then there's this IPO is really bad. So we decided to determine how much benefit we would get if we would have like perfect static information. So we're currently having a tool that deduces a kind of perfect static information for a certain set of input-output pairs on your program, and that then tells you how much optimization potential you're losing because you don't have good static information. And that is, we're currently evaluating that one on different HPC benchmarks, and we see like 5 to 10% speed up just by having a couple of static annotations that we're missing. And then finally, as soon as you work with runtime libraries, you get into the problem that runtime libraries could potentially do whatever, right? A runtime library call could do whatever. And yet we have to start annotating our runtime libraries in a way that makes sense. So we have already in C++ attribute cons, we have attribute pure, we have other things, other attributes that we can add to convey some facts about what will happen here, what is the effect that could happen or prevent effects from happening. And that is like automatically generating those because the compiler already derived them when compiling the runtime library. We could actually expose that information to the user of the runtime library later on. That is something that is currently planned. If you're interested in any of them, please contact me. Now, we evaluated the whole thing. So first we did the inter-procedural optimizations I showed earlier, so attribute deduction, which is function attribute deduction about is an argument read only, write only, all of that. Is a argument no alias in the function, all of that information is we used transitive call sites to enable that for parallel programs, and we used transitive call sites to do variable privatization, which turns out to be exactly argument promotion, which is this instead of sending something by reference, sending it by value through a function. Now we also have constant propagation enabled, but I don't have many numbers for that. Let's look at the first examples I showed in the very, very beginning. That at the very beginning I showed only the left two numbers, which is the slowdown you have between a sequential version and a parallel version executed with one thread. Now I have the different optimization combinations here, always with sequential and parallel version executed with one thread. So if we, like the Lulesh benchmark, we actually get a speed up executing the parallel version with one thread compared to the sequential version. Now, sometimes we can't get rid of the whole overhead of this could theoretically be the runtime. This could theoretically be some optimizations that we're currently missing. We only do 2 inter-procedural optimizations here, right? Now, sometimes we get a significant speed up, which can be explained, when you ask me, I can tell you. And if you remember the 2.5 times slowdown we had for the SRAT benchmark, it disappears, it disappears completely, right? So there is no slowdown anymore if you do argument propagation and deduce attributes properly. So this is really good, and it turns out that also holds for other benchmarks. So we can go on and have different other benchmarks that show exactly the same behavior. So you get rid of all the overhead you introduce, and you can enable optimizations. Now we looked at a real-world example. So this is one loop simplified from the Lulesh Cocos version, which is actually used, right? With the OpenMP backend, we optimized that loop and only that loop, not all the others, only that loop. What we wanted to do is there's this array here with initialized with constants, and it's used inside this parallel function. And we wanted to propagate all those constants into the parallel function, right? That seems reasonable to do. Now, to do that, we need everything I showed you earlier and more. So I had to actually annotate some runtime library calls in a way that makes sense. I had to specialize some values here and some passes. And then at the end, the last 0.8 percent improvement. That is transitive call sites into 2 IPOs that we enable. So that gives you a 0.8 improvement. But the other things are also interesting because that is something we're currently missing, which we can do. And this is only for one of the parallel loops in there and not for all of them. Now, to conclude, what you've seen is that we lose a lot of performance when we parallelize programs. So we lose a lot of sequential performance, which we then try to get back by scaling. But that is just something that it doesn't really make sense. And we should first try to get our performance on par, and then we start to optimize it for parallelism. Transitive call sites is a lightweight abstraction on top of the abstraction we already have, and it simply enables inter-procedural optimizations for parallel programs and for sequential programs. You can, though the inter-procedural optimizations we have right now are just not good enough, so I have different proposals to improve those, which you should look at if you're interested. And if you do all of that, you can actually get sequential-like performance for parallel programs executed with one thread, which had a slowdown of more than 2 before. So thank you for your time, and if you have any questions, I'm here.
So there's a microphone set up in the middle if you want to line up there, or I can run the handheld to you. Any questions? Yes.
So the shortcomings you said and you showed in the IPO optimizations, actually, I mean, just putting all the parallel stuff aside, that affects OS and OZ, right? Because there we have a much lower inline threshold, so
yes.
we rely on those optimizations
yes.
more, right? So that's, I guess, a further incentive to work on this. And
for all the people that are interested in those builds and those optimization levels, yes, they should probably look at the RFC for the attribute deduction, which already tells a lot of shortcomings, and then there are other things in interprocedural optimizations that are just not, they're just not good as they are right now. So we should work on those. And if you're interested, I have to work on those anyway. So
yeah, this is really cool work.
Yeah.
Any others?
Has anyone tried the approach in the LLVM client context of doing the splitting after part of the optimizer rather than doing it in the front end?
Yes. There are a couple of approaches that do that do basically late outlining. One of them is currently discussed in the form of an RFC on the mailing list and later in our BOF. So if you're interested in that, you should come. That is just a bigger effort. Abstract transitive call sites is minimal. Improving IPOs makes a lot of sense for different reasons. And combining those two is also minimal effort and it's sound. While doing late outlining comes with a lot of reasoning you have to do to make sure that it's not that you everything is sound, everything is good. And depending on how you do it, you don't get the optimizations for free either. You have to teach the optimizations, your barrier, your region, intrinsics, mean, and all of that. So it's here you have to teach them what a transitive call site is. There you have to teach them how you separate your parallel code from your sequential code. Tapier is an approach where you get optimizations for free, but you're limited in what you can represent. So we're currently exploring that space, and where we will end up is unclear. This is a short-term solution to give us a lot of benefit right now, and then we can still, it will never hurt us to do this in the future. So I'm not saying this will replace anything.
So the BOF at 4:30.
The BOF is at 4:30, I heard.
We have time for more. If anyone has another question? No? All right, thank you, Johannes.
Thanks.